After studying this module, you shall be able to know about the item validity index, calculate various types of correlations between items and total test score, judge the type of correlation that needs to be computed according to the item response types, calculate the Pearson product moment correlation, learn about the biserial correlation, and statistically calculate point biserial correlation. During the construction of psychological test, the effectiveness of each individual test item has to be determined. The process of evaluating each item is called item analysis. It plays the role of selecting the best items from a pool of tryout items. The item validity index is one of the various methods of assessing item analysis. It is a statistic designed to provide an indication of the degree to which a test is measuring what it is intended to measure. To determine the validity of an individual test item, the correlation value of each item score with the total score on the test is calculated. If both the item score and the total test score are in graduated fashion, Pearson product moment coefficient of correlation is calculated. When one variable is continuous in nature and the other is actually continuous but forced into dichotomy, the biserial correlation is calculated to determine the validity index of the item. In another case, if a continuous variable needs to be correlated with a true dichotomous variable, the point biserial correlation is the method of choice. It is to be noted that the higher the correlation, the more accurate or valid the test item is. On the other hand, test items with 0 or very low correlation value or negative correlation value should be removed from the test. Item analysis, item validity index. Item analysis is an integral part of the test development process. It is the method by which each individual item is scrutinized and tested before included in the final test. Various different types of methods are used for item analysis. The three main technical methods most commonly used are item discrimination index, item difficulty index, and item validity. In the previous module, the statistical methods to compute item discrimination index and item difficulty index have been described. This module heaves light on the item validity indices of the item analysis. It is to be noted that when each item of the test effectively discriminates on the basis of a particular quality or ability between high and low or strong and weak persons of a group, then only it can be called valid. Thus, the discriminative power of the item is an indicator of it being valid too. Each item has to be discriminative besides being fully valid. Broadly defined, validity of any measuring instrument is the level of accuracy with which it measures what it purports to measure. Based on this, the item validity index is a statistics designed to provide an indication of the degree to which a test is measuring what it intends to measure. The calculation of validity indices of test items is essential, as validity of the entire test depends on the validity of each item, and independent validity of items is the validity of the whole test. Statistical methods of finding item validity index. Theoretically, the item validity index tells how the responses of an item are related to the total test score. Statistically, the item validity index is calculated by finding the correlation value of each item score with the total score on the test. The total score excludes the response to the item in question. The type of correlation method used to find item validity depends on the response scores of an item. The three types of Pearson's correlations used for calculating item to total correlation are the Pearson product moment correlation, the Pearson biserial correlation, and the Pearson point biserial correlation. Pearson product moment correlation. Assume a 10 item scale in which each item has 4-point Likert type responses ranging from completely false being 1, somewhat false being 2, somewhat true being 3 and completely true being 4. To compute the item validity index, responses to each item need to be correlated to the total scores for the test takers. This is an example where both the variables are continuous in nature. In such cases, the Pearson product moment coefficient of correlation is the statistical tool of choice for calculating the item validity indices. In this, both the variables are in interval or ratio measures. The formula for calculating the Pearson product moment correlation coefficient is R is equal to n multiplied by summation xy minus summation x multiplied by summation y, the whole divided by under root n summation x square minus summation x whole square, the whole multiplied by n summation y square minus summation y square, where n is the number of score pairs, x and y is the equal paired scores, summation xy is multiply x by I and summation x, sum of all the x scores, summation y, sum of all the y scores, summation x square is the square all x and summation y square all y and summation x whole square is the sum of x and summation y square is the sum of y. For example, let us try to find the item to total correlation for item 7 in the following data set. Item score on a 4-point Likert type response to that of total score is 3 item score 28 total score, 4 item score 38 total score, 4 item score 36 total score, 2 item score 12 total score, 3 item score 22 total score, 3 item score 22 total score, 4 item score 16 total score, 1 item score 11 total score, 4 item score 31 total score and 3 item score 27 total score. Let's put these values in terms of x and y, where x is the item score and y is the total score. Item score for 10 subjects x is 3, 4, 4, 2, 3, 3, 4, 1, 4, 3. The total score, which can be represented as y for the 10 subjects, are 28, 38, 36, 12, 22, 22, 16, 11, 31 and 27. By summing all the x values, summation x is 31 and by summing all the y values, summation y is 243. On squaring the x score, we get x square. X square for these 10 subjects is 9, 16, 16, 4, 9, 9, 16, 1, 16, 9 and summation x square is 105. By squaring all the y values, the y square value for all the 10 subjects is 784, 1444, 1296, 144, 484, 484, 256, 121, 961, 729. Thereby, summation y square becoming 6703. Multiplying the x and the y scores for these 10 subjects, we get the xy value for the 10 subjects. The xy value for these 10 subjects are 84, 152, 144, 24, 66, 66, 64, 11, 124 and 81. Summation xy therefore is 816 and the sample size is 10, therefore n is equal to 10. Applying the formula of Pearson R that we have stated, therefore by substituting these values in the above mentioned formula, we get R is equal to 10 multiplied by 816 minus 31 multiplied by 243, the whole divided by under root 10 multiplied by 105 minus 31 square, the whole multiplied by 10 multiplied by 6703 minus 243 square. Therefore, R is equal to 8160 minus 7533, the whole divided by under root 1050 minus 961 multiplied by 67030 minus 59049. Therefore, R is equal to 627 divided by under root 89 multiplied by 7981, which is equal to 627 divided by under root 710309, and the under root of 710309 is 842.7. Therefore, the value for R becomes 627 divided by 842.7, making it 0.74. Thus, the item to total correlation for this item 7 is 0.74. The biserial correlation. When one variable is measured in a continuous fashion and the other variable is actually a continuous variable but which has been forced into dichotomy, the biserial item to total correlation method is appropriate for computing the item validity index. In such a case, responses of a forced dichotomous variable represent a false dichotomy. A false dichotomy is an arbitrary decision to force a continuous variable into a dichotomous one. The most typical example of a forced dichotomous variable is an item scored as pass or fail, that is, yes or no, like or dislike, agree, disagree, etc. Passing or failing is an example of a true dichotomy. Achievement can be thought of a continuum ranging from those who pass with exceedingly high scores and down to those who fail miserably. In the normal procedure of test scoring, we reduce a continuous variable to pass or fail dichotomy according to the arbitrarily set particular cutoff score by the test taker. Similarly, if a score on a 4-point Likert type scale, completely disagree, disagree, agree, completely agree, are grouped only in two categories ranging between completely disagree and completely agree, this represents a false dichotomy. The formula for calculating the biserial correlation is RBIS is equal to MP minus MQ divided by sigma t, the whole multiplied by PQ divided by mu, where RBIS is the biserial correlation coefficient, MP is the median of higher group, MQ is the median of the lower group, P is the equal ratio of higher group people, Q is the equal ratio of lower group people, mu is the height of side or arm of the ordinary which divides P and Q into two parts, and sigma t is equal to standard deviation of the test. Let us look at an example to calculate the biserial correlation. Compute the biserial correlation for the following data set that represents the distribution of scores on item 7 in an aptitude test. Group 1 represents the frequency of candidates rating item 7 as strongly agree, and group 2 represents frequency of those who rate item 7 as strongly disagree. Scoring for item 7. Let us look at the range of scores and what the frequencies of these scores are in group 1 and in group 2. For this range of score 55 to 59, group 1 frequency 1, group 2 frequency 1. For the range of scores, the following are the range of scores: 50 to 54, 45 to 49, 40 to 44, 35 to 39, 30 to 34, 25 to 29, 20 to 24, 15 to 19 and 10 to 40. The group 1 frequency who rated this item as strongly agree is 1, 1, 3, 4, 6, 7, 12, 6, 8, 2, making the sum 50, whereas for group 2 who rated these ranges as strongly disagree are 1, 0, 2, 2, 3, 6, 9, 4, 3, 2, making the total a 32. So, if we need to arrange it in a tabular form, we may arrange it as scores 55 to 59, 50 to 54, 45 to 49, 35 to 39, 30 to 34, 25 to 29, 20 to 24, 15 to 19 and 10 to 14. The midpoint of these intervals are 57, 52, 47, 42, 37, 32, 27, 22, 17 and 12. The frequencies for group 1 are 1, 1, 3, 4, 6, 7, 12, 6, 8, 2 making the sum 50, and for group 2 the frequencies are 1, 0, 2, 2, 3, 6, 9, 4, 3, 2 making the sum 32. The total F or the total frequency for group 1 and group 2 combined is 2, 1, 5, 6, 9, 13, 21, 10, 11 and 4 making the total 82. Fx, if we multiply frequency with the midpoints, we get 114, 52, 235, 252, 333, 416, 567, 220, 187 and 48, summation Fx being 2424. X is equal to capital X minus capital M is 27.44, 22.44, 17.44, 12.44, 7.44, 2.44, minus 2.56, minus 7.56, minus 12.56 and minus 17.56. When we square the midpoint ranges, x square is equal to 752.95, 503.55, 304.15, 154.75, 35.35, 5.96, 6.55, 57.15, 157.75, 308.35 and Fx square is 1505.9, 503.55, 1520.75, 928.5, 498.15, 77.48, 137.55, 571.5, 1735.25, 1233.4 making summation Fx square 8712.03. MP, the mean of group 1 is equal to 57 multiplied by 1 plus 52 multiplied by 1 plus 47 multiplied by 3 plus 42 multiplied by 4 plus 37 multiplied by 6 plus 32 multiplied by 7 plus 27 multiplied by 12 plus 22 multiplied by 6 plus 17 multiplied by 8 plus 12 multiplied by 2 the whole divided by 50 making it 29.60. The mean of group 2 MQ is equal to 57 multiplied by 1 plus 52 multiplied by 0 plus 47 multiplied by 2 plus 42 multiplied by 2 plus 37 multiplied by 3 plus 32 multiplied by 6 plus 27 multiplied by 9 plus 22 multiplied by 4 plus 17 multiplied by 3 plus 12 multiplied by 2 the whole divided by 32 making it 29.50. Calculation of sigma. M is equal to summation Fx divided by n which is equal to 242 by 82 equal to 29.56, where m is the mean, x is the score, f is the frequency and n is the total number of observations. Therefore, sigma is equal to summation Fx square divided by n which is equal to under root of 8712.03 divided by 82 which is equal to 10.31. See the value of mu from Garrett 1958382 for area from mean 0.61 to 0.50 which is actually equal to 0.11. We get mu is equal to 0.384. Now, putting these values in the formula for calculating the biserial correlation, correlation coefficient R bis is equal to MP minus MQ divided by sigma t multiplied by PQ divided by mu. Substituting values, we get 29.60 minus 29.50 divided by 10.31 multiplied by 0.61 into 0.39 divided by 0.384, which is equal to 0.10 multiplied by 0.61 multiplied by 0.39 divided by 10.31 multiplied by 0.384, which is equal to 0.02379 divided by 3.95904, which is equal to 0.006. Thus, the item to total correlation for this item is 0.006. The point biserial correlation. The Pearson point biserial correlation item to total correlation coefficient is applied to those cases where one of the variables is continuous in nature and the other represents a true dichotomy. A true dichotomy is one where the categorization really has only two possible alternatives for a single item. Male or female categorization of gender represents a true dichotomy where subjects are either grouped as male or female categories. Other examples of true dichotomies where the criteria are exact, married or unmarried, right or wrong, delinquent, non-delinquent, psychotic, normal, colorblind, normal, etc. The formula for calculating the point biserial correlation is Rp bis is equal to MP minus MQ divided by sigma multiplied by under root PQ, where Rp bis is the point biserial correlation coefficient, MP is the mean of the first group, MQ is the mean of the second group, P is the proportion of the first group, Q is the proportion of the second group, and sigma is the standard deviation of the total score. Let us look at an example to calculate the point biserial correlation for item 5 of a 10 item test. There are 15 subjects in total. Their test criterion are 25, 23, 18, 24, 23, 20, 19, 22, 21, 23, 21, 20, 21, 21, 22. The item number 5 scores are 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. Therefore, out of the total N9, the number of passing students are 9 and number of failing are 6. MP is equal to 25 plus 23 plus 23 plus 22 plus 21 plus 23 plus 21 plus 21 plus 22 divided by 9, making it 22.23, and MQ is equal to 18 plus 24 plus 20 plus 19 plus 21 plus 20 divided by 6, which is equal to 20.33. P is equal to 9 divided by 15, 0.60, and Q is 6 divided by 15, which is equal to 0.40. Sigma is 1.82. Therefore, applying these values in the point biserial correlation formula, we get the coefficient of point biserial correlation Rp bis is equal to 22.23 minus 20.33 divided by 1.82, the whole multiplied by under root of 0.60 multiplied by 0.40, making the value 0.54. Thus, the item to total correlation for this item is 0.54. Some important considerations. Item assessment interpretation using any of the Pearson correlation coefficients is similar to the usual interpretation of this statistic. For all three types of correlations, the value of coefficient ranges from -1 to +1, with negative values indicating that the item is negatively correlated to the other item in the test, and the positive values depicting a positive correlation of item in question with the total test scores. Items having negative correlation with the total test scores are not desirable, as it indicates that the test is not measuring a single construct or ability. Items with low correlation show that they do not correlate well with the remaining items and should not be included in the final test. It is best to have items having mid-range high positive correlation, that is from plus 0.50 and above with the total score. Such items are retained in the final scale. It is essential to understand that computer software does not recognize the difference between a false dichotomy and a true dichotomy. It is up to the researcher to know the difference and specify the correct analysis. If the point biserial correlation is calculated when the biserial was supposed to be, it will underestimate the true strength of the relationship. Summary. An item analysis is a statistical method used to determine the quality of a test by looking at each individual item or question and determining if they are sound. It helps identify individual items or questions that are not good questions and whether or not they should be discarded, kept, or revised. Validity of any measuring instrument is the level of accuracy with which it measures what it is supposed to measure. Statistically, the item validity index is calculated by finding the correlation value of each item score with the total score on the test. The three types of Pearson's correlations used for calculating item to total correlation are the Pearson product moment correlation, the Pearson biserial correlation, and the Pearson point biserial correlation. When item scores and the total scores are both continuous in nature, the Pearson product moment correlation coefficients are calculated to find the relationship of each item with the total score on the test. When one variable is continuous in nature and the other is actually continuous but forced into dichotomy, the biserial coefficient is calculated to determine the validity index of the item. If a continuous variable needs to be correlated with a true dichotomous variable, the point biserial correlation is the method of choice. It is best to have items having mid-range high positive correlations, that is plus 0.50 and above, with the total score. Such items are retained in the final scale.